Hello, thank you all for joining today. My name is Julia Hylton. I'm finishing up my PhD at the Colorado School of Mines. I actually just submitted my thesis last week, so. Oh, stop. Thank you. So all of my graduate research has been focused on studying how biochar interacts with hydration products and strength development in cementitious systems. This is going to be more of an academic presentation, but I think we can apply a lot of the findings to future applications in industry. We know that biochar can be beneficial from an environmental standpoint, but it's really important to understand how the material itself is interacting, so that we can optimize it for the best carbon reduction. Quick overview, I'm going to be talking about a little bit of Biochar 101. Probably going to cut this part because we have kind of talked about it a little bit. Then I'll discuss our mix design and how we mill the biochar before integration. And then I will discuss the model that Seth nicely introduced for me for determining what the important characteristics are for strength development. And then I'm going to talk a little bit about biochar and cement hydration and some of the carbonation that we see in cement mixes. So very quick overview. Biochar, it's a carbon negative material if we don't sell off the carbon credits. That allows us to include it in cement and offset more of the carbon dioxide equivalent than the biochar itself. Basically, if we include a ton of biochar into a concrete application, we can offset more than 2 tons, more than 3 tons of carbon dioxide equivalent. Depends a lot on the feedstock, depends a lot on the process, but that's kind of our mission statement going forward. One of the reasons that biochar is carbon negative is because the carbon that is originally in your feedstock, i.e. the little forest graphic that I've got, is not oxidized either through natural decomposition or by combustion. So all of that carbon is locked into place in the carbon. It's additionally stable. Its stability increases once you add it to concrete. So all of the research that I'm going to be talking about today was done on cement mortars. Allows me to do some more lab scale prototyping. But we only use biochar as a cement replacement. We find that that's the biggest bang for buck. Cement is our most carbon intensive component. Let's get that out of there, put a carbon negative material in there, and we see a much higher carbon offset that way. I will say, like others have said before, biochar has a really high water demand, so we do need to increase our superplasticizer content. We're able to get comparable workability and compaction with the addition of additional superplasticizer, but it is definitely a consideration going forward if there's ways that we can tailor the biochar to reduce that water uptake. The biochar itself is a really porous material. When we receive it from a commercial producer, it comes usually in a like roughly wood chip shaped particles that are very, very porous. You can see in the left image those large pores. Those are left behind from the cell wall of the actual feedstock, but those are hollow and take on a lot of water and add a lot of porosity to our final mix. We try to mill below that macro porosity, so we're left with a very fine particle that does not have those large pores in it. That reduces the water uptake and allows it to integrate a little bit better as a cement replacement. Excuse my very artistic graphic, but when we use biochar as a partial cement replacement, we're actually doubling the volume of particles that we replaced. So we take 10% of the cement mass out, we replace it with 10% mass of biochar. Biochar is about half as dense as cement, so it decreases the spacing between all of our particles during mixing, increases our particle packing, and also increases the rate of dissolution of the cement grains themselves. So I think that would be the mechanism that we would point to for why we're seeing such high strength gains by using less cement. This is the 28-day compressive strength data that was introduced earlier. We collected 16 different biochars, milled them all to roughly 10 microns below the size of cement grains, and replaced 10% of the cement mass with biochar. Despite using less cement powder, we were able to see comparable or significantly improved compressive strength after 28 days of curing compared to our control. We tried to get our hands on as many diverse kinds of biochar as possible. We looked at softwoods, hardwoods, agricultural feedstocks, pyrolyzed a couple different ways: slow pyrolysis, fast pyrolysis, as well as gasification. And with the addition of superplasticizer and milling to below that cement size, we were able to see pretty remarkable strength improvements. But now the question is, clearly biochar is not all created equal. What are our differences that we're seeing, and how can we maximize the benefits we are seeing? So I characterized the 16 biochars really every way I could think of. We looked at the pyrolysis conditions, we looked at the physical characteristics, the surface area of the particles, the ash content. I think it's important to note that the biochar has only a handful of chemical components. You have your carbon content, your oxygen content, a little bit of nitrogen, a little bit of phosphorus, a little bit of sulfur, and then everything else is considered ash content or inorganics. That's where you get your silica, your calcium oxide, some of the other inorganic materials that we're interested in. Some of those are soluble, some of them are not, worth more research. The moisture content is something we are going to talk about a lot, not only the moisture content of the biochar when you add it into the material, but also how much moisture it can hold on to while you're mixing. We also looked at the chemical composition, chemical content, the surface chemistry, and we're able to create a multivariate model that predicted the compressive strength that we were seeing for a 10% cement replacement using our 16 different chars. The three key characteristics that we found was the initial saturation content, just the ratio of how wet the biochar was when we added it to how much water it can take up total. We found that by lowering that saturation content, your biochar is able to absorb more water, densifies your cement matrix, makes sense, get a tighter microstructure, increase strength. Similarly, we saw that more soluble silicon increases compressive strength. Also checks out, we know why. And then, more puzzling, we saw that the oxygen to carbon surface ratio was detrimental to compressive strength development. This is a parameter that tells us about the functional groups on the surface of the biochar. It can lead to differences in water uptake and polarity. Definitely still a region of additional concern. Still need to figure out exactly what that mechanism is and how it's affecting our compressive strength gain. But we see really good correlation between the measured compressive strength that was shown a couple slides ago and the predicted compressive strength using these three parameters in this model. So this gives us a way forward on what we need to optimize, what we need to look into for understanding how biochar is interacting with cement systems. Another area of research that we work on is understanding the degree of hydration. How much of our cement has been converted to hydration products. It's a whole different world once you start adding new additives. A lot of things can change, and a lot of our old techniques don't quite give us the right picture. So normally we would take a hydrated cement paste, thermally decompose it, and measure the mass loss and correlate that to how much hydration products have been developed. Then we compare that to a late age sample and we say, okay, great, this is 75% hydrated. We can go forward predicting strength. Biochar has a lot of volatile content and will begin to decompose additionally above its production temperature. So this kind of muddies the picture of our mass loss. So we were seeing really high mass losses with our cement paste samples and trying to figure out, is that increased hydration? Is that the biochar decomposing? What's going on? So we employed TGIR, which basically just takes the gas that's decomposing, tells me what kind of gas it is, and then we can back calculate from there. So this blue line, the dark blue line, shows our mass loss. The there we go. This first water vapor loss, this is our pore water. Then we get into CSH decomposition by kicking off water molecules from the CSH. This is where the calcium hydroxide decomposes. And then we see some areas of overlap before we get into this carbonate, calcium carbonate decomposition area. For biochars, we're able to separate out both the gases that are decomposing and also subtract out what is attributed to the biochar itself decomposing. And using those measurement techniques, we're able to see that the biochar pastes are hydrating slightly less than a normal cement. This makes sense a little bit. We're replacing 10% of the cement mass, so we expect a little bit less chemically bound water in that hydrated paste. But we're also seeing quite a bit of calcium carbonate formation. I will say when I set up this experiment, I sealed all the samples so that they're not sorbing CO2 from the environment, from the room, from the atmosphere. So this, to me, points to the cement matrix actually reacting with the biochar, the carbon in the biochar, since there isn't an external source. I think it's worth additional research to figure out, is this carbonation beneficial or not for cement mortar like strength development? Are these carbonates filling pores and increasing our strength and bonding the biochar to the actual cement matrix? Or are these carbonates forming and stealing calcium that would otherwise be converted into calcium hydroxide and calcium silicate hydrate? So the main mechanisms that we point to for strength development are the filler effect. That's that increased particle packing by including a lower density insoluble biochar in place of cement. We know that some biochars, if they have a high silica content, can act pozzolanically and increase our strength that way. Still an area of future work for how carbonation is playing a factor. And then internal curing is cited quite frequently for biochar improving strength in concrete. For the milled biochar, we have very, very fine pores. So we're not seeing the desorption behavior from those biochars that would benefit durability and shrinkage. But it's still possible that with larger pores, that could be a potential mechanism. I do want to leave us with the potential for this research. We can look at two distinct biochars, a woody biochar that's high carbon content, low inorganic content, and then a rice hull biochar, my personal favorite, that is low in carbon but high in silica. If we replace enough cement to make the entire mortar carbon negative, there are going to be different replacements based on the different carbon contents for each of the biochars. But we can see that we get comparable strength improvement by replacing 48% of the cement with a rice hull biochar that's been milled after 56 days of curing. The woody biochar is not quite as impressive. We do have to replace a lower content of cement, but are able to meet our structural minimums for compressive strength after 7 days. This is with a really high water reducer dosage, and yeah, they turned out fantastic. I am really motivated by these findings, that if we choose biochar for its actual properties in cement systems rather than trying to maximize our carbon offset, we can make really good carbon negative concrete. Yeah, thank you.